Forget everything you think you know about computers. Seriously, we're not talking about a slightly faster laptop here. This is quantum computing, a total, fundamental reinvention of how we calculate things. It's designed to solve problems that are, well, literally impossible for even the biggest supercomputers on the planet.
And hey, this isn't some far-off sci-fi dream. The commercial quantum ecosystem, it's on track to blow past $1 billion in 2025. This revolution isn't coming, it's happening right now, and the stakes could not be higher.
So, what does that $1 billion get us? Well, how about a totally new timescale for discovery? Just imagine shrinking the pipeline for developing life-saving drugs from a matter of decades down to just a few days. I mean, that's the kind of game-changing transformation we're talking about. Now, you can bet that this incredible potential has kicked off a fierce global race. China, for instance, has thrown something like $15 billion into a massive state-led push. They're aiming for total dominance in a technology that's going to redefine whole industries and even national security for the next century.
But to really understand this race, we need to know what we're all running towards. What does winning in quantum computing even look like? It's definitely not about checking your email faster. It's about making the impossible possible.
All right, to get this, we need to know the difference between two really key milestones. First, you've got quantum supremacy. You might remember Google claiming this back in 2019. Their Sycamore chip solved a problem, a totally useless one, by the way, faster than any supercomputer could. It was a cool proof of concept. But the real prize, the goal that changes everything, is quantum advantage. And that's using a quantum computer to solve a useful, real-world problem better than any classical machine ever could. That's the finish line everyone's racing towards.
So how do we get there? Well, we have to go way beyond the simple ones and zeros, the bits and bytes of today's computers. The crazy power of quantum comes from actually harnessing the strange and wonderful rules of quantum mechanics itself.
You see, in your phone, every piece of info is a classical bit. It's just a simple switch that's either a 0 or a 1, on or off. Pretty simple. But the quantum version, the qubit, well, that's where things get really weird. A qubit can be a 0, it can be a 1, or, incredibly, it can be both at the exact same time.
This both-at-once ability is called superposition, and it's the secret sauce behind a quantum computer's incredible power. Think of it this way. A few classical bits can only represent one number at a time, but thanks to superposition, the same number of qubits can represent every single possible number all at once. It's a mind-bending, exponential explosion in processing capacity. You know, a great way to think about this is a spinning coin. While it's up in the air, before it actually lands, is it heads or tails? In a way, it's kind of both, right? It exists in this blurry state of all possibilities. That's superposition in a nutshell. Now, the second piece of this quantum magic is called entanglement. This is a deep, almost spooky connection between two or more qubits. Once they're entangled, their fates are linked together. If you measure the state of one of them, you instantly know the state of its partner, even if they're on opposite sides of the universe. This idea was so bizarre, so out there, that it famously bothered Albert Einstein himself. He dismissed it as spooky action at a distance. But you know what? This spooky connection is an absolutely critical resource that makes complex quantum algorithms actually work.
Okay, so with these two powerful new tools, superposition and entanglement, where's this revolution going to hit first? Let's take a look at the industries that are really on the brink of a complete transformation.
First up, pharmaceuticals and chemistry. Our regular computers, even supercomputers, really struggle to accurately simulate how complex molecules behave. But a quantum computer, because it's a quantum system itself, is perfectly suited for the job. It lets researchers find a molecule's most stable state, which is a critical step in designing new drugs and materials with just pinpoint precision. Next up, materials science. I'm talking about designing revolutionary materials literally from the ground up. Imagine creating room-temperature superconductors that could transform our entire energy grid. And recent breakthroughs in new hardware are already proving this isn't just a fantasy. They're unlocking even more computational power to simulate some really complex physics. And of course, there's finance. Get this, current fraud detection systems can have a staggering 80% false positive rate. Quantum algorithms promise to build vastly more accurate risk models. But there's also value right now. Quantum sensors, like hyper-accurate atomic clocks, are already being used to perfectly sync up high-frequency trading systems. Now, all of this sounds incredible, right? Almost too good to be true. So what's holding us back? Well, we need to talk about the current reality of quantum hardware, which is, and I'm not exaggerating, arguably the toughest engineering challenge humanity has ever taken on. So what's the catch? Why don't we all have quantum laptops sitting on our desks right now? Well, the answer comes down to one fundamental, relentless enemy. And that enemy is called decoherence. You see, those quantum states of superposition and entanglement, they are unbelievably fragile. The slightest vibration, a stray magnetic field, even a tiny change in temperature can cause the qubit to decohere, to just collapse back into a boring old classical bit, completely wiping out the entire computation.
This fragility is what defines our current era, the NISQ era. That stands for Noisy Intermediate Scale Quantum. Basically, the hardware is just too noisy. It's filled with errors. We have a tiny window of time to compute before decoherence kicks in. And to even have a fighting chance, these machines have to be kept in these massive refrigerators, colder than deep space.
So the path forward is clear. We have to move from this noisy, error-prone NISQ era to the era of fault-tolerant quantum computing, or FTQC. The secret is something called quantum error correction. It's this really clever strategy where you use many fragile physical qubits all working together just to create a single, stable, reliable, logical qubit that can finally resist decoherence and do some useful work.
So while all the engineers are off battling decoherence, the rest of us need to start preparing for the day they win. Because the arrival of a real, fault-tolerant quantum computer, it creates some urgent deadlines and some incredible new opportunities.
The most immediate threat is one you can't even see. Right now, adversaries are hoovering up and storing our encrypted data. They can't read it today, but they're betting that in a few years, a powerful quantum computer will be able to crack it all wide open. This strategy is called harvest now, decrypt later, and it makes the quantum threat an urgent problem for today. And because of this, governments are not waiting around. They've set hard, non-negotiable deadlines for everyone to switch to new, quantum-resistant encryption. By 2031, all the high-priority systems have to be migrated. By 2035, everything else has to be secure. The clock is definitely ticking.
But look, with a great challenge comes great opportunity. This entire new industry needs a brand new workforce. There's an intense demand for people who can bridge the gap between physics, engineering, and computer science. And, well, the salaries for these specialized roles show you just how valuable and how rare these skills are right now.
From fundamentally rewriting our digital security to creating entirely new career paths and solving some of science's hardest problems, this technology is going to change everything. So the only question left is, are you ready for the quantum revolution?